Here is our second practice problem for intermolecular forces for organic chemistry. Question 3 says the graph below shows how the vapor pressure of different organic molecules change as the temperature changes. The line at 101.3 kilopascals on the graph indicates the external atmospheric pressure. The vapor pressure of 4 different organic substances which are similar in molecular mass versus temperature are indicated. The 4 curves A, B, and C, or A, B, C, and D, represent organic compounds belonging to the following homologous series. A straight chain alkane. I just want to talk about that. When we mention a straight chain alkane, we mean an alkane that does not have branches on it. A branched alkane, so obviously that has a branch, a primary alcohol, and an aldehyde. So those are the 4 compounds that we are working with. A straight chain alkane, a branched alkane, a primary alcohol, and an aldehyde. So let's have a look at this graph. So yeah, we notice that we've got temperature in degrees Celsius on the x-axis, we've got vapor pressure in kilopascals on the y-axis, and there is your 101.3 kilopascals, which is standard atmospheric pressure. That's part of your STP. Okay, so we have these 4 curves, A, B, C, and D, but they did not say that, which curve is for which homologous series. So that's probably something that we have to figure out on our own based on the intermolecular forces that the homologous series contains. 3.1, however, says define the term vapor pressure. Again, just like boiling point, this is a definition which you learned in grade 10. So it is the exact same definition from then. So here's a definition. It is the vapor pressure exerted by a vapor at equilibrium with its liquid in a closed system. (3.2) says the vapor pressure of compounds A and B are compared. 3.2.1, write down the independent variable for this investigation. So remember, independent variable relates to what you are changing in the experiment. So if we look at the 4 compounds that we're working with, we had a straight chain alkane, a branched alkane, primary alcohol, and aldehyde. But we are specifically focusing on A and B. So A is a straight chain alkane, and B is a branched alkane. So it's actually given in that order, right? A is a straight chain alkane, B is a branched alkane. They are both alkanes. So we cannot say homologous series because homologous series is the same for A and B. What's different though would be, we can say the type of compound because they are 2 different compounds, but let's be more specific. We could say chain length. Now chain length would matter because one is a straight chain alkane, the other is a branched alkane. One has a branch, one doesn't. So we can say chain length. We can also say surface area, and I would think surface area is the most correct answer here. Because remember, what happens with branches is that the more branches a compound has, the smaller its surface area. So when compounds have branches on them, they sort of curl in towards itself, making the compound smaller in size. So it occupies less space. So the most correct answer here, among the few that you can have, but the most correct answer would be surface area. I'm just going to fill in the other answers that you could have here. We could even say chain length, or we could say type of organic compound. Now, 3.2.2 says, explain the difference in the vapor pressure of these two compounds. So, firstly, if we look at our curves of the graph, A appears to have the highest vapor pressure out of all 4 compounds. Then B has a lower vapor pressure. And remember how this relates to boiling point is that it is the opposite. Since A has the highest vapor pressure, it means that it actually has the lowest boiling point out of all these compounds. So A is actually expected to be the branched alkane. A is the branched alkane, and B would be the straight chain alkane. So that information was not given to you. They didn't necessarily say this was the specific order. They didn't use the word respectively when they mentioned A, B, and C. Well, A, B, C, and D. But judging from the information that we have, a branched alkane should have a lower boiling point than a straight chain alkane. Therefore, it should have a higher vapor pressure. So A is actually, and maybe it's good if we can name this, A is the branched alkane, and B is the straight chain alkane. Okay, so we need to compare these two, and you can see that the explanation here is 4 marks. So you would definitely get a mark for mentioning which compound or which letter represents which compound, since that information was not given to you at the start. Let's start off by saying A is a branched alkane while B is a straight chain alkane. Now, you can either choose to go ahead and talk about compound A or talk about compound B. I'm just going to speak about A here. Since A is branched, we know that it's going to have a smaller surface area. Okay, so it becomes more spherical. So we can say compound A has a smaller surface area. Than compound B. And with regards to a smaller surface area, what happens is that it has weaker intermolecular forces. So the smaller the surface area, the weaker the intermolecular forces. So A will have weaker intermolecular forces than B. Remember, it's a comparison. Since it has weaker intermolecular forces, it should have the lower boiling point, but remember, you are answering in terms of vapor pressure, so you would say, therefore, A has a higher vapor pressure than B. Because vapor pressure and boiling point are inversely proportional. And this is actually evident on our diagram where we see that here compound A does have the highest vapor pressure. So vapor pressure is on your y-axis. Now 3.3 says write down the boiling point of compound D. So where are we going to find boiling point of compound D? Remember your definition for boiling point. It's the temperature at which the vapor pressure is equal to the atmospheric pressure. So here's our atmospheric pressure, which is 101.3 kilopascals. And all we have to see is exactly where the graph of D intersects that line. Now, it is not exactly at 120. It's a little before that. So here's 120. It's slightly before that. So I would say 119 degrees Celsius. So for questions like this where you need to read off values from your graph and the values are a little confusing where some might think it's 120, some might think instead of 119 it's 118, you would have a range for questions like that. For this question, the range was 118 to 120. 3.4 says which one of the compounds C or D is the alcohol, and give a reason for your answer. Now here's the thing. From what we are left with, C and D are going to represent the alcohol and the aldehyde. But if we compare the intermolecular forces that an aldehyde has and an alcohol has, we know that an aldehyde has dipole-dipole forces, whereas an alcohol has hydrogen bonding. Hydrogen bonding is stronger than dipole-dipole forces. So we are expecting this alcohol to have the highest boiling point, meaning the lowest vapor pressure. If we look at C and D, we notice that the points at which they start, it's compound D that has the lowest vapor pressure. So compound D is going to represent the alcohol. And your reason is that it has the lowest vapor pressure. (3.5) says the vapor pressure of compounds C and D are now compared. Which variable must be kept constant in this experiment? Now here's the thing, right? They belong to different homologous series. So the intermolecular forces are not the same. But because they belong to different homologous series, what needs to be kept the same has to be their molecular mass. So they need to be the same size. They need to be a comparable size so that we can actually compare them together. So what should be kept constant for C and D is molecular mass. Because think about it logically. It would be unfair for you to compare an aldehyde that has 7 carbon atoms in its parent chain to an alcohol that only has 2 carbons. These compounds need to be more or less the same size in order for you to compare them together. Okay, so that is molecular mass. Okay, so now we have 3.5.2. It says refer to the types of intermolecular forces to explain the difference in vapor pressure between compound C and D. So just remember, we said that compound C is the aldehyde and compound D is the alcohol. Now let's start off by first talking about the type of intermolecular forces that each compound has. Okay, so we start off by saying C is an aldehyde that contains dipole-dipole forces, and D is an alcohol that has hydrogen bonds. Now, since we've mentioned the type of intermolecular forces that they have, we now need to mention which one is stronger, and obviously we know it is hydrogen bonding that is stronger. So let's mention that. So hydrogen bonding is stronger than dipole-dipole forces. Now, once you mention which intermolecular force is stronger, you then need to refer to energy. So we say more energy is required to overcome the intermolecular forces in compound D than in compound C. Now, if this was about boiling point, we would conclude and say, therefore, compound D has a higher boiling point than compound C. But this is now about vapor pressure. So we can conclude and say, there's one of two things. We can either say, therefore, compound D has a lower vapor pressure than compound C, or you can say, therefore, compound C has a higher vapor pressure than compound D. So it's up to you. But for us, it looks like we've been comparing D to C, so I'm just going to conclude and say that, therefore, compound D has a lower vapor pressure than compound C. Please remember to like, subscribe, and turn on your notifications for more content.